warm-up question that I want us to take a look at where this is very similar to sort of a Calc 1 question where we're simply being asked to come up with the equation of a tangent line. So let's just read through that. We've got a rock that's being whirled around on a string and it's sort of, kind of made up, I guess. Why isn't that right? Oh, come on. All right, hang on just a second, folks. All right. There we go. So there's the equation of the motion of this rock, which holds for time greater than or equal to 0, if it's continued to be tied to this string. But what we're going to say is that at time t equals pi over 2, we're going to go ahead and cut this rock. And ignoring gravity, I don't want to introduce gravity into this problem. We're going to imagine, in fact, let's go ahead and look at the GeoGebra for this before we solve it. If you were to click on that link, it should pull up this three-dimensional space here in GeoGebra. And I don't know, folks, I'm taxing my computer here, sharing screens, recording, and everything, so I don't know if I'm going to be able to rotate this. You should be able to rotate that, maybe not if you've got Zoom going. But there you can see in blue, I've got the traced motion of this this rock that's attached to the string. So you can imagine it being whirled around, I guess. So at time pi over 2, let me double check that, folks. I might have to modify that. Sorry, make that 2 pi in the notes. Sorry about that. At time t equals 2 pi, we're going to cut the string. And so then what would happen to this? Well, we would expect the rock to fly off in a straight line, at least initially. So it might be that, eventually if this is on Earth, gravity will take over. But at least for a small period of time, you could imagine when you cut the string, this rock is going to fly off tangent to the curve at that point. So really what we're asking you to do here is to come up with the equation of a tangent line. Okay? So let's go ahead and do that. So remember that in general, when we're looking for the equation of a line, we're going to give a line of the form r is equal to r naught, which is some initial point, plus t times v, where we think of v as a direction vector. So we're going to need two things here to be able to describe this new curve, and let's give it a new name. So I'm going to put r of t with a little subscript t there, so we've got that is a tangent line. So to compute this tangent line, we need to find out, first of all, a position on this line. And I think the easiest way to do that is what? What should we do to find a point on this line?
Plug in 2 pi?
Yeah, so we'll plug in 2 pi, the time where this curve starts, or the time where the string is cut, because we know that point is also on this curve as well as on this line. So if we find r of 2 pi, and boy, I hope all these lines line up. I had to change this several times, folks, so hopefully everything lines up here. But regardless, we're going to plug in that time value, whatever time value is given, but we're using 2 pi here. So 3 times 2 pi, comma, 1 plus 2 times the sine of 2 times 2 pi, comma, and then the time value of 2 pi. And so if we crunch everything out here, this would give us the ordered pair 3, 1, 2 pi, or the position vector 3, 1, 2 pi. That's where this line is then cut. Okay? And so what's going to happen? Well, the rock is going to continue moving tangential to the curve at the point where the rock was cut. And so this direction vector is really just r prime of 2 pi. Anyone have any questions on that? That's kind of the new content that I wanted to, we hadn't looked at an example like this in class, so I just wanted to cover this. Does anyone have any questions about what I'm doing there? Why we're saying the direction vector on the line that we're trying to find is the derivative of the position function, evaluated at 2 pi. Any questions on that?
I do have a question. Could you have chose t equals 0 instead of 2 pi?
Yes. let's see here. Because this is 2 pi periodic, we could have plugged in 0 for time, Matt. That would have given us the same the same point. In the x and y coordinates.
It's not,
Yeah.
coordinates not periodic.
Thank you, Dustin. Yeah, in the x and y coordinates, that would give us the same position. And I guess I could have started this problem right at time t equals 0. It's cut. But I wanted to be able to. So I wanted to be able to look at the curve of this in space, and so you can see that this should have. I think it should have the same x and y coordinates. There we go. Well, it's going to rotate very slowly on me, but I think it should have the same x and y coordinates there because of the 2 pi periodicity of the x and y coordinates, but not the same z coordinate. And I guess as far as creating the problem, I could have had it cut right at time t equals 0, but then we wouldn't really have a graph to see how the tangent line comes shooting off this. Let's just go ahead and since we're talking about this curve again, here is the tangent line that we're going to find that I've put in red here. And you can see that that's as if it was cut right at that point, as opposed to if the curve continued on in 3 space, which would look like that. So if it hadn't been cut, it would continue along the dotted line, but because it's cut right at time t equals 2 pi, it continues along the red line. Are there any questions about this? I mean, I was gonna wait till we actually had the equation of that red line there, the tangent line, but now that we're looking at it, let's see if are there any questions about this physical phenomena? Now, of course, there's no gravity involved here, right? And so we're just treating this as if maybe you're standing on the moon and you do this, or something like that, where you don't have to, where gravity is a little bit more negligible. Or you could think of this, at least for a small increment of time, it would travel in a straight line, basically a straight line path before the acceleration due to gravity was large enough to start pulling it down, or the impact of the gravity was enough to pull it down. Yeah. Any questions on that, folks? Okay. So I do think this is a little bit different than things we've seen before. So it's a nice application of the derivative of the position function. So let's go ahead and find the derivative of this position function. And by the way, what's a more natural name for that? That's our velocity of that position function. Oops, sorry, no prime there. Which is our velocity of that position function, which is just what in this case? It would be 6 cosine 3t, oops, sorry, minus 6 sine 3t, comma, the derivative of the sine is the cosine with the chain rule, so we get 4 cosine 2t, comma 1. And so if we evaluate this at the time value 2 pi, the velocity function of this curve at 2 pi is, well, let's see here. If we plug in 2 pi into the sine, we just get 0. If we plug it into the cosine, we get 1, so that's 4, and then 1 for that z coordinate. So now we can go ahead and give this function rt of t, and we found both an initial vector and we found a direction vector, which the new material, I mean, really the only new material here is to say that the direction vector is simply the velocity vector. Because when you cut this string, the object continues to fly tangent to the curve at that point, in that direction. Okay, so I'll go ahead and just write it in vector form here. This would be the vector 3, 1, 2 pi plus t times 0, 4, 1. And there you've got the direction curve, the tangent line to the curve at the point 2 pi. Any questions out how we were able to come up with this tangent line, folks? I hope everything lined up, folks. I changed this probably a dozen times over the last 3 days. So if the curves that I put into GeoGebra don't align with that, at least for the curve I've given up here, we've basically found the equivalent of this problem. Okay, I'm not sure whether those curves all line up in GeoGebra at this point. Any questions on that? All right. So let's go ahead and look at some applications now of section 14.3. And so hopefully this is the same problem that we were going to look at last time that we didn't get to. We've got a baseball being hit 3 feet above home plate with initial velocity of 80 feet in the x direction, 80 feet in the y direction, 80 feet per second, I guess. And so you could compute the magnitude if you wanted to for this velocity, right? You could say that the magnitude of v naught would be the square root of 80 squared plus 80 squared if you want to talk about exactly what the speed of this baseball is as it leaves. So I'll let you check that if you want to find out what the magnitude of this. The other thing is, since those two are equivalent, we would assume that this baseball is leaving home plate. So let's see here. Let's go ahead and give ourselves an axis. We're up here at 3 meters, and it's leaving home plate at an angle of 45 degrees. Okay. So what I want to practice is building our position and velocity functions from the acceleration function, which is, so last time I gave you a position function and we went ahead and found velocity and acceleration functions by taking the derivative, and that's really nice, but in the real world you're not given a position function. Instead you base it off the sort of initial statuses with Newton's laws of gravity. So in this case, we would say that our acceleration as a vector valued function, well, there's going to be no acceleration on this ball in the x direction, but the acceleration, we are going to have an acceleration of negative 32 in the y direction. So here I'm considering x the horizontal and y the vertical. Be careful here, folks, because as we move in between 2 and 3 dimensions, we will adjust where y is in these problems. Okay. So that means that to find our velocity function, we're going to take and integrate the acceleration function. And I'm just going to go ahead and say, so if we integrate it termwise, this would give us c1 comma negative 32t plus some other constant, where we know that if we plug in t equals 0, so that's for our velocity here, velocity function, and we know that if we plug in time equals 0, we're supposed to get out that as our initial velocity. So that means that our velocity function, given that initial condition, is going to be 80 comma negative 32t plus 80. So that describes the velocity of this curve, this trajectory, or the path of this baseball. Okay. So then to find the position function, we'll integrate the velocity function. And in this case, I'm going to write it this way. I'm going to go ahead and give the answer as 80t comma minus 16t squared plus 80t. And then I'm going to put plus some constant vector. Okay. Normally, we'd always write plus that constant vector, but that's a little bit awkward to do in this first case where we had a 0 for our acceleration value. So then I don't want to have a total of 3 different constants I'm dealing with. But normally you should write a constant vector after you integrate. And then what's our initial displacement here, folks? Where is the ball when time starts? What's our initial displacement?
0.3.
So our initial x displacement is 0, and our initial y displacement is at 3 feet. So that's the vector. That's the initial vector 0, 3. Great. So then that gives us, so how do we go ahead and find out what c has to be? Well, notice that that's when time is equal to 0. So we know that s of 0 needs to equal the vector 0, 3. And so from there we would deduce that c would have to also be 0, 3. And so we get that our s of t is 80t, comma, minus 16t squared plus 80t plus 3. So folks, one thing to point out is notice that when we do this, you're going to get that parabolic motion that you would sort of expect. I mean, if you looked at the path of this baseball as I drew it up here, you would expect to have something of a parabola. That is the parabola that models the height of the baseball at any point in time. Okay, and that should look very similar to some of the Calc 1 problems that you did. Okay, but now we can sort of take all of those traditional Calc 1 problems and now work with them with this vector valued function. And that's a little bit more realistic because at any point in time we give not only the height, but we also give the current position. Or excuse me, the current horizontal position, so the x displacement as well. Okay, so that's satisfied number 1 there. B asks the question, how far does the ball travel horizontally? And it looks like I'm going to run out of room here. Sorry, folks. B asks the question, how far am I going to travel horizontally? And so what do we need to do here? Well, notice the ball will stop. No, notice, first of all, if this thing had a constant, if our position function had a constant vertical component, if the y height didn't change, then in this model, when we hit this baseball, it would just always keep going in the x direction, right? What's going to cause it to stop adding more to the x direction? Well, that's when our model breaks down, which is when the ball hits the ground. So really what we're going to do to answer this is we're going to ask, when does the ball hit the ground? Okay, so now at this point, I mean, we've got an acceleration function, we've got a velocity function, and we've got a position function. So you've got all these functions that you've built based on these initial bits of information. Let's go ahead and answer the question, though. Which of these are we going to use when we ask the question, when does the ball hit the ground? I mean, if the ball hits the ground, what do we know about the current state of things? There's only really one piece of information we know. What is that?
The y
elevation is 0.
positive to negative, or hit 0.
Yeah, so the y-coordinate, the elevation there needs to be 0. Very good. Okay. So to do that, we're going to set, I'm going to go ahead and call this the horizontal component, excuse me, the vertical component of displacement equal to 0. So really what we're doing is we're going to go ahead and set this, I could call, if I wanted to, it might be nice to call this thing y of t. So we're going to set y of t equal to 0. So that would happen when minus 16t squared plus 80t plus 3 is equal to 0. And if you solve this, you could just use the quadratic formula. I don't think that this doesn't look like this factors or doesn't factor. You could do complete the square on it, and you would get two roots, one of which is negative, and the positive root happens at, yeah, I guess these are pretty messy, so this happens at 5.04 seconds. So 5.40 seconds into the flight, this ball hits the ground again. How are we doing, folks? So if we then ask the question, how far in the horizontal direction did this ball go, we're going to use that same time value. So this point right here is just going to be this vector right here, which is x of 5.04, comma, and I could write y of 5.04, but we've just said that we found that 5.04 by setting the y component equal to 0. So now if we find 80 times 5.04, that would be our x of 5.04, and that comes out to be 403 feet. We could ask another question like, what's the maximum height of the ball? And there's a couple different ways we could go about this one. The maximum height of the ball is reached at this point right here, at this vector right here, right? So I could try to find the position vector But there's another vector that's going to be easier to work with, and what is that at this point in time?
Velocity equals 0.
Well, so let's be careful here. The velocity of this ball doesn't equal 0.
Well, doesn't it at its highest point?
Well, the vertical.
In fact, yeah. So the vertical speed is 0 there. I think that's what you meant. That the vertical speed is 0 there. But another way to look at it is that this vector, the velocity vector, is going to have 0 as its y component. Okay. So for this, for C, we're going to go ahead and set the the vertical component of v of t to 0. So that's going to happen when negative 32t plus 80 is equal to 0. And then we can find that time value. That time value comes out to be 2.5. 2.5 seconds. Okay. So, folks, we don't actually need to find the entire blue vector here, but we do know that we wanted the y component to be 0. We don't know what the x component is, but we don't need that to answer this question. But you could say, how fast is the ball traveling horizontally when it reaches its maximum height? And that might be kind of an interesting question, because then you could talk about how much speed that it's lost during those first 2.5 seconds of travel. Okay.
Also, for answering C, what I was doing last night was I just looked at the position function.
Yep.
And I looked at the second one, the y component.
Uh-huh.
And I saw that I just do negative b over 2a, and that finds the maximum of the height.
Yeah. So Dustin, everyone hear what Dustin said. That's another way you could go about doing this problem, and that makes use of the fact that the vertical component of the position function is a parabola. And so what you were doing is you were using the vertex formula for a parabola. As a reminder, though, the vertex formula comes from, I guess you could derive it other ways, but it's most easily found from calculus by taking the derivative of that vector or that function, setting it equal to 0, and then solving for t, which is where you get negative b over 2a. So that way would certainly work, although that way would not apply in other instances if this was not a parabola, where this method of thinking about where does this thing have a 0 vertical velocity component, that will apply to many other instances. Yeah, but that's a really good observation. Yeah, thanks, Dustin. Okay, so now what do we do? Well, we want to say, well, how high is it? So now we're going to go ahead and we're going to plug t equals 2.5 where, folks? I mean, one of the hard things about this is we've now got so many, we've got 3 functions, and each function has 2 components. We just found that 2.5 is an interesting time value, but what are we going to do with that?
Plug it into the y value for the position function.
Exactly. Plug it into the horizontal component of the position function. So we could then find y of 2.5. So that's going to be negative 16 times 2.5 quantity squared plus 80 times 2.5 plus 3. And if you crunch that, you get 103 feet. Okay. So the next thing I want to do is, I don't think I want to answer D, if that's okay. Let's just give ourselves a strategy for D. Okay. So we're asked the question, does the ball clear a 200-foot fence? Or excuse me, does the ball clear a 20-foot fence that's found 380 feet beyond home plate? So how are we going to answer this?
Well, you could find the t values for those x and y coordinates with the position function, and then see if that's equal to when it lands, or when the ball lands on the ground.
When the ball lands on the
For
ground.
example, I would set 80t equal to 380 because I know that the x value is going to be 380 feet out, and then I could solve for t, and then t would, in that case, would give me 380 divided by 80, which would be 4.75. So then I could find the height 4.75 seconds in by plugging it into the y component of position function, which gives me 22 feet.
Did everyone hear Dustin's explanation of that?
Yes.
So folks, what we're going to do, is exactly what Dustin said, is we're going to find the time when x of t equals 380 feet. So we're going to find where in the trajectory, do we have a x coordinate of 380 feet. Then we can go ahead and plug that result into y of t, which will tell us the height at that point in time. And as long as that height in that point of time is greater than 20, then the baseball will clear the wall. Any questions on that, folks, before we move on?
I have a question. Back in I think it's C, when you solve for t.
Yes?
Oh, no, I don't know what it is, but I think you were trying to solve negative 16 squared plus 80t plus 3, and then you just solved for t.
Uh-huh.
And you got 5.04. How did you get 5.04? Did you use a calculator or?
Yes. So you could use complete the square, or you could use a calculator. In this case, it doesn't factor, so you can't try to factor that quadratic.
Just a calculator.
Yep.
All right. Thank you.
Uh-huh. Okay, so folks, let's do this again, and we're going to do it now in 3 dimensions here. So in this case, and we started looking at this problem last time. Let's go ahead and call this this direction here in the y-axis. We'll call that north, and we'll call this direction in the x-axis. We'll call it east. And so then we've got our vertical in the z component. Okay. So in this case, what we're going to do is we're going to fire this cannonball at an initial angle of 30 degrees. But we've got a crosswind as a force on this, and so we would find that this cannonball isn't going to continue along just the, it's not going to stay in the xz plane. Instead, that crosswind is going to move it out so it lands somewhere in the xy plane, not on the x-axis. So we have all the information we need, given that we were told how the acceleration due to the crosswind behaves, and the fact that we'll use the constant for gravity as 9.8 meters per second squared. So at that point, we can give the acceleration function. Okay. So there's going to be no acceleration in the x direction. By the way, it might be that your crosswind isn't due north. You might have a crosswind that's behaving like this, in which case you would have to break up the acceleration function into x and y components. Okay. But to kind of simplify things, and in fact, maybe you would choose I would choose my orientation based on the direction of the crosswind just to make life a little easier. But in this case, the crosswind's blowing due north, and so that's not going to affect the trajectory of the ball in the x direction. But it is going to add, it's going to cause the ball to accelerate in the y direction at a constant 3.6 meters per second squared. Also, that crosswind is not going to affect its vertical velocity component, but what will? Gravity will, and gravity acts opposite to well, it acts in the negative direction, so we get 9.8, negative 9.8 for the acceleration in the z direction. Okay. So let's go ahead and find what our v naught is and then our s naught. Sometimes these are given for us, sometimes we have to find them. In this case, we're simply told the speed of the cannonball at 300 meters per second. And initially, so the cannonball is fired in the xz plane, and so it has no y velocity component. So this is going to be, so all the velocity is going to be distributed amongst the x direction and the z direction. And so let's break this down into the x and z components. So the z component of the x component of the velocity is going to be 300 times, and so if we think of this right here, for our angle, the x component is going to be 300 times the cosine of 30 degrees. There's nothing in the y direction, and then we get 300 times the sine of 30 degrees in the z direction. And in this case, what's our initial displacement? Well, we're told that this is fired, I think it says negligible height. Let's see here. Maybe it doesn't. Let's assume that it's fired at negligible height above the ground. Oh, over flat ground. Well, it doesn't say negligible, so we'll just assume that. So our initial position is 0, 0, 0. So notice I could, you could go ahead and give this some other position other than the origin. You could give it a height, which would be natural. I don't think you'd really want to give it a x and y component, because it would just make sense to then just shift your origin.
It says cannonball is fired from the origin.
From the origin, great. Okay, great. Thank you, Dustin. Yeah. Okay. So we've got our initial displacement here, and let's go ahead and find both the velocity and position functions. So our velocity function, v of t, integrating would be, and then just applying our constant, would be 300 cosine of 30, which, let's see here, the cosine of 30 is the square root of 3 over 2. So that gives 150 square root of 3, comma, and then for our y, we just have its constant, which is 0. That's that's not right. Sorry. Integrating, sorry folks, I was looking at the wrong place. Integrating that would be 0.36 t, comma, then negative 9.8 t plus 300, well, 300 times the cosine of 30, the sine of 30 is a half, so that's 150. Any questions, folks, how we came up with the velocity function? So I integrated it and applied the initial condition simultaneously.
Where did the 0.36 come from?
Yeah, so let's go ahead and write that out. So folks, you don't need to erase anything if you don't want to, but let me write that out. Our velocity function is the integral of the acceleration function. So in the first one, we'll just get some arbitrary constant. So I'm integrating this function right here, Aya. So in the first position, we just get, 0.36 t plus some other constant, and then negative 9.8 t plus some other constant. And then if we apply this initial condition, remember that happens, I write 0, that implies when t equals 0. And so because of that, we would have 300, square root of 150 square root of 3, comma, 0.36 t, and then comma negative 9.8 t plus 150. Yeah, great question, thank you. So remember, I was integrating that acceleration function. Okay. So now we want to go ahead and find the position function, and to find the position function, we're going to integrate the velocity function. So that's going to give me 150 square root of 3t. We'll just do it this way. 0.18 t squared, comma, and then negative 4.9 t squared plus 150 t, plus some constant function. But what's the constant function going to be in this case? Well, we know that our initial displacement needs to be 0, 0, 0. So if I plug in a 0 for all these t's, I need to get the output of 0, 0, 0. So that tells us c has to be the constant function 0, 0, 0. So now these problems are similar to what we had before, only we now have these 6 different, or we have potentially 9 different coordinate functions to be working with. So you do want to be careful with that. But let's go ahead and let's see what we were asked for. We were asked for where does the cannonball land. So to do this, notice that the well, to figure out where the cannonball lands, what do we want? This is actually a similar question to what we asked in the two-dimensional case. The cannonball is going to land when its vertical component is what?
0.
When its vertical component is 0 there. So to find out where it lands, we're going to set the vertical component of s of t equal to 0. So that happens when negative 4.9 t squared plus 150 t is equal to 0. This one I can pretty quickly solve. We could factor out a t, so we get negative 4.9 t plus 150. So that happens when t equals 0, but that's not the one. That's not the root we want. Or at t equals well, let's just do it. I don't have it in front of me. At we don't want that one. Or when t equals negative 150 divided by negative 4.9. If somebody wouldn't mind giving me a decimal approximation on that. I think is that 30.6 seconds? Is that what I had?
Yeah, that's what I got.
At 30.6 seconds. Any questions on that, folks, for when the ball lands? So now we can give the x and y components, and so to find where it lands, we're just going to evaluate s of 30.6, and so we'll take 150 square root of 3 times 30.6, comma, 0.18 times 30.6 squared, comma, and then I'm just going to go ahead and say what's this last component going to be, folks?
Zero?
Definitely, 0. That's where we came up with the 30.6 by saying that the vertical component has to be 0. Okay. And so, let's see here. It looks like I didn't jot this one down. So, if we went ahead and got a decimal approximation for that, where do we get? So help me out, folks. I'll grab a calculator, but if you've got it, shout it out.
I got 79.50 for the X.
79.50, good. And then for the Y,
16,854.
16854.
I got.
That sounds a little high.
18,635 as the total distance.
What's that?
I got 18,635 as the total distance.
Great. Let me just double check that, Matt. I just want to make sure I got 168, Matt. That's not 18. That's
what I got as well.
That's 0.18 there. So I think 100. So close. I think you just had a decimal dropped. So I think 168. We'll call it 169 feet, basically. Okay. Now, if we want to ask the question, how far from the origin, or how far did the Cannonball travel in terms of the distance along the ground, we would just simply take the magnitude of s of 30.6. So we would take the square root of 7,950 plus 169 squared plus 0 squared. And it sounds like, Dustin, did you compute that already?
I had 7,952.
Where did the previous bit, where did the 0 at the end come from on S of 30.6?
Yeah, great question, Cedric. So how did I get the number 30.6 to begin with?
You set the vertical component of the position function to 0.
Aha. So we got the number 30.6 by saying, what do I need to plug into the function so that z comes out to be 0? So I didn't have to evaluate that one. Yeah, great question. Other questions, folks? So we get 7,952 feet. Is that what somebody said?
Yes.
Do I have a second on that, folks? Math by democracy here. All in favor?
That's what I got.
Okay, great.
Feet or meters?
Oh, good question. I think we're in meters here because we use 9.8. Thank you. Was that Hannah who said that? Allison. Who said that? Hosanna. Thank you, Hosanna. Sorry. Okay. Let's go ahead and answer that last question. In order to correct for this, what angle do we need to launch this cannonball at? So if we want to, so the question here is if we want it to land on the positive x-axis. Okay? So what we're going to do now is we're going to think of launching the cannonball. It's still going to go upwards at the same angle, but we're going to launch it initially at a some angle, and we'll call that angle theta here, heading in the, well, if this is north, we'd want to have it angling south of east there. Okay? So here comes our trajectory. It's going to go this way, and then it's going to come out this way. And so if you were to look at the trace in the xy plane, we want it to make a, well, we don't know whether that shape's going to be. It's going to end up being a parabola, but we want it to look like that. So it'll start off with the angle, the initial angle we have it's going to be dipping below the x-axis, but eventually that acceleration is going to force it back so that by the time it lands on the x-axis. Okay? So here's how I want you to think about it for this problem. I'm going to think of the velocity component. I'm going to break it up into two different parts, and I'm going to call it the vertical component and the ground component. Okay. In this problem, the vertical component, we're not going to change the fact that we're not going to change our initial pitch angle, so it's still being fired upwards at 30 degrees. And we're not going to change the initial velocity of this cannonball, so it's going to have the same vertical component. So the vertical component is still going to be that 0, 0, 150. But the horizontal component is now going to be, so what did we have left? So before, originally, originally if we'd broken this up, we would have said that the ground component, before we added this angle, was 150 square root of 3 comma 0. That was the ground component. And then the vertical component was 0, 0, 150. But now what we're going to do is we're going to take that ground component with the magnitude of 150 square root of 3, because it's a unit vector, that's its magnitude, 150 square root of 3, and we're going to disperse that, break that up into southerly direction, or y direction and an x direction. So the ground component of this is now going to be 150 square root of 3 cosine theta, comma, let me give myself a little bit more room there. So it's going to be 150 square root of 3 cosine theta, comma, 150 square root of 3 sine theta, comma, and then 0 for the, because there's no vertical component in the ground, just the ground component. So that's how we're going to break up our velocity function. Does that make sense, folks? I found that part a little bit confusing. The key here was to say that the vertical component of velocity doesn't change. And neither does the magnitude of the ground component isn't going to change either. What is going to change is the direction of that ground vector. And so what we can do is, now that we've added in this angle, there's going to be both a y component to the ground vector and an x component. Okay. By the way, go ahead.
Why did the gravity, the negative 9.8 t, disappear from the vertical component?
Oh, I'm sorry. Let me. Great question. Let's see. I'm sorry. I can't see people.
Danielle.
Great question, Danielle. I'm sorry. This is our v naught, our initial velocity vector. Okay, everything else about the problem is remaining the same. We still have the same. We still have the same crosswind. We still have the same acceleration due to gravity. We still have the same initial condition. The initial position vector. The only thing different is our initial velocity vector. Yeah, great question. So I made a mistake there. I put v of t, and I should have put v naught. So good catch there.
Why is it 150 root 3 and not 300 for the cosine and sine on the vector?
Yeah, because that's because it still has. So 300 is the magnitude. It's the speed at which the cannonball leaves the cannon, and so in terms of a vector, part of that vector is going to be in the vertical direction. And that component hasn't changed. We're still shooting it at the same pitch, and the magnitude hasn't changed. So we're still going to have for the vertical component, that's going to stay. That hasn't changed.
I see.
So before we had let's see, where are we? Before we had this. So you could think of these two together as being our ground component. And so if you take the magnitude of that initial vector, that magnitude is that 150 square root of 3. That magnitude hasn't changed. What has changed for this ground vector is the direction of it. So if you were to take the magnitude of this part, you still get 150 square root of 3. And then if you were to take the magnitude of, add to that and find the magnitude of the sum of those two vectors, you still get 300. Yeah, great question.
That makes sense.
Yeah, and I found that to be probably the most confusing part about this problem. Yeah. Okay, so now that we've got that, we can sort of, if you want to, you could start over from acceleration. So let's just start over from acceleration. Your a of t hasn't changed at all, so I'll just jot it down from before, 0.36, negative 9.8. And so if you do the integration on this, and the integration won't change, all that's going to change is your initial velocity vector. So if you do the integration and then take into account this is your v naught, as opposed to the vector we had before we tried to adjust for the crosswind, we're going to have 150 square root of 3 cosine of theta, comma, 0.36 t plus 150 square root of 3 sine of theta, comma, and then the y component hasn't changed one bit, so we get negative 9.8 t plus 150. And so then if we find the new position function, we get s of t is equal to the square root of 150 square root of 3 cosine of theta times t, and it's an extra factor cosine of theta there, comma 0.18 t squared plus 150 square root of 3 sine of theta t, comma, and negative 4.9. This part hasn't changed one bit. T squared plus 150 t. Now, because the z component hasn't changed here, folks, what's the one thing about this problem where the ball hits the ground that hasn't changed? Notice that the x component and the y component and the z component will have all changed, but what hasn't changed as far as this ball hitting the ground?
The time it takes.
Yeah, did everyone hear what Hosanna said? The time it takes to hit the ground hasn't changed. So now we can go ahead and find S of 30.6. So that still needs to give us, and now what do we want? Well, we want it to, it's going to have a height component still of 0. And we want it to lie along the x-axis here, right? So this is that S of 30.6 vector. That's that vector right there. And so what else do we know? Besides the fact that we want the z component to be 0, we also want the
Y.
We also want the y component to be 0. And we don't know exactly what this is, I guess, although I guess we could go ahead and plug it in. We know that it's going to be the same same total distance, so that would be the 7952. So now we could solve either of these two equations, equating those positions or equating those positions, plugging in 30.6 for the time. This one would give me two solutions, but I'd throw out one of the solutions. But this one's probably the easiest to solve for. So we'd have 150 square root of 3 times the cosine of our angle theta times that 30.6 seconds needs to equal 7952. Or that the cosine of theta is equal to 7952 divided by 150 square root of 3 times 30.6. And then if we take our inverse cosine function, and here's where we're going to have to be a little bit careful because I don't think this is going to give us exactly what we want. So if somebody wouldn't mind doing this in degrees, giving us the inverse cosine function, the value that we get when we take the inverse cosine of this.
Did anyone else get a domain error?
Yeah, I got domain error because it's not in the domain of cosine inverse.
I did too.
So we'll have to calculate the inside and then do like.
Is the x position going to be the same?
The x, yeah, great question. Who asked that? Yeah, Kevin, the x position isn't going to be the same. It's not 7950. But because the other two components, so the distance this cannonball travels from the origin has to remain the same.
I think the domain error is just the calculator because I just evaluated everything that's inside of that parentheses, so 7952 over the quantity 150 root 3 30.6 all multiplied together, and it gave me 1.00023. So I think it's supposed to be 1 on the inside.
Well, it's not gonna come out to be exactly 1. So let's see here. Why is this off?
Could it be
So
because the 7952 is the estimate?
Yeah, the 7952. Here, I'll calculate it with the exact value that I calculated, and I'll tell you what it is, because that's true. That is an estimate. The actual value is 79518996.
So folks, I'm sorry to do this, and I'll see if I can come up with a quick explanation for this later. But if we subtract 1 from that, that's going to put us back into the domain of the cosine. And when I do that, it gives us an angle of 89 point, 89.98 degrees. And then
it makes sense because when you initially did it, yeah, never mind. Actually.
And so then if we
really close to the y-axis.
yeah, and so then if we were to subtract 90 from that, that gives us approximately that angle shift there. Okay. Sorry, where is that picture? That's not the right picture. This picture here. So let me do a little bit more thinking about how we can get that into the right position there. But I do think we need. I mean, this number does need to be bigger than the. This is going to give us a quantity, a ratio that's bigger than 1, and so you can't use the inverse cosine on it initially. But I haven't. I apologize. I haven't thought all the way through how we adapt. Remember, there's some limitations to using that inverse cosine function, and so I haven't thought all the way through how we're going to adapt that to get us that angle.
Would the -1 be almost like a rotation?
Exactly. Exactly.
Okay.
Yeah, but I haven't thought it through a nice explanation to explain why we're doing all of that. So I'll see if I can come up with that.
I've been lost for a little while now. How did you drive that equation where your mouse is, or not my mouse, never mind. 150 root 3 cosine theta 30.6 equals 7952.
Okay. So we said that when we plug in 30.6, we need to get this vector out.
Oh, okay.
You know what, folks? I'm thinking. I think I do have a mistake here. I apologize. Although I don't think that this distance is going to be the same as the same distance that it travels. So instead, I apologize here. Let's instead of working with that equation, what we're going to do is we're going to take this second one. This one we do know for a fact we're on the y-axis, and so we're going to take 0.18 t squared plus 100. Well, we're going to plug in 30.6 for time. Times the sine of theta, and we want that to give us 0. So folks, I think I made a mistake here saying that the distance it traveled should be the same. That doesn't make sense, because if you fired it with the wind versus firing it against the wind, it's not going to travel the same distance from the origin. So that was a mistake to use that number from before. So we don't know what this coordinate is, and so we can't set this component equal to that coordinate. Everyone understand my mistake? You don't want to talk about it anymore? So now if we go...
I don't think I quite understand.
Yeah, so Cedric, I said that it's got to travel the same distance, total distance from the origin, and that is not true. So if you think about it, if you fired the cannonball into the headwind, it's going to travel a shorter distance than if you fired it in the opposite direction, so with the headwind. So we don't know this number, but we did say we're choosing theta so that we end up on the x-axis here. So we don't know what this component is, the x component is of this vector, but we do know the y component of this vector is 0, and of course the z component is 0 because that's when it lands. So folks, my mistake was to say that it travels the same distance, and that is not true. So let's go ahead and finish this out then. If we set this, we've set this to 0 here, so we have that the sine of theta is equal to negative 0.18 times 30.6 squared all over 150 over the square root of 3 times 30.6.
If I did it right, I still got an error. Domain error.
Let me check here. I got it to work out okay. Whoever asked that. So double check that you put parentheses around this entire denominator. And when I get this, I get an angle of negative 1.214 degrees, and that's the correct answer. So whoever got the error, double check that. Was that you, Phoebe?
Yeah, you were saying that for the exam, a calculator wouldn't be necessary, but
Yeah.
I found that in like the practice I needed a calculator quite often. Are you gonna choose easier numbers to like?
Yeah. So this is not going to be an exam question.
Okay.
Yep.
Cool. Just wanted to
So
double
it's
check
still my
because I
intent.
don't have
Yeah.
a calculator.
So it's still my intent that you don't need a calculator for the exam. You may find it helpful to have one, but if so, you can only use a non-graphing one.
Yeah. Okay. Just.
Yeah. So this would not be an exam question.
Okay.
Yeah.
I just needed to know if I needed to buy one before
Nope.
the exam. Okay. Thank you.
Okay.
Where did you get that final data?
Yeah. So I went ahead and took the inverse cosine, or excuse me, the inverse sine of that expression.
And what is that number? One.
Negative 1.214. I guess it should be negative 1.215 when you round it.
Okay.
Is anyone else having trouble getting this? Did anyone get that number? Let's check that first. Yeah. Is anyone having trouble getting that number?
So there's one thing I'm hung up on. The x component of the s, or of our position function of 30.6.
Yes.
I understand that wasn't supposed to be the same thing because of the headwind, but what did we end up doing with it?
Well, nothing, because what we were doing here is we were equating the different component functions to their supposed values, and we didn't know what to equate this equal to. Because we didn't have, we didn't know what to. So now, if you wanted to, you could find out where on the x-axis it landed by substituting this in for your theta, and now plugging in 30.6 for time, and you could find where on the x-axis it lands.
Okay, so then since we weren't aware of what x was, we moved to the y equation.
Right, and my whole reason for initially picking the first component functions was because if we had known what to set that equal to, I just thought it was a little bit easier to work with.
Okay.
Yep.
Would you be better off saying that it's 1.15 degrees south of east instead of having the negative?
Yeah, that's another. So one thing when we originally set this up, notice that we need the sine value to come out to be negative, so that we're working against. So if we called this north is the positive direction, and so this is got to angle us south. So we were expecting the angle to come out to be negative, but yeah, you could say then another way to say that is that theta, or let's go ahead and orient it. We want to aim 1.215 degrees south of east for a final answer on that.
I have a question, like earlier on when we found the first part, could you find like the point where that cannonball lands originally and then move in like the negative direction, like kind of like clocking your origin around just by using the point of the landing? Or would that not work because of the wind, like what we ran into earlier?
Well, so I think, Matt, what you would be answering is sort of a different question. It would be if you wanted to move the cannon so that you were still firing in the same direction, and then it would land on the x-axis.
Okay.
Is that what you're saying?
Yeah, I guess so. I guess that's.
And you could if we thought of this as a engineering problem, you could resolve there's two ways you could resolve this problem. If you fire the cannon and it doesn't hit what you want, you can move the cannon, or you can adjust how you're firing it. So our question was how could we adjust how we're firing it? But yeah, you're right that you could have moved the cannon and had the same, and that would have been probably an easier question to answer, but anyway, we wanted to try this one.
Yeah.
Great question. Okay, folks, I want to do one more thing here, and unfortunately, I can't figure out how to not have it show you my solution to this, so I apologize it's showing here. What I want to say is that if you've got a motion with a constant magnitude, then the tangent vector is always orthogonal to your position vector. Okay? So the classic example for this is if we were to have just in two space, if we were traveling along a circular path here. So let's take, this would be my position vector at some time value. And notice if I were to compute the tangent vector, look at what we expect that to look like. That's what we'd expect the tangent vector to look like. Let me put that in a different color there. Now I'm not talking about the magnitude of that tangent vector. That'll depend on the parameterization choice, how quickly we're spinning around the curve. So the magnitude of that tangent vector is going to change. But notice that it's not a coincidence on a circular path. Everywhere along a circular path, the direction vector is always, the position vector is always perpendicular to the velocity vector. Now, it doesn't have to be a circular path for that to happen. There are other paths where that could happen. So what this theorem is saying is that when would it happen? And the answer is whenever your position vector has a constant magnitude, the magnitude of that position vector isn't changing, then your velocity vector, so that's our position vector, there's our velocity vector, that will always be orthogonal to our position vector. So let's go ahead and prove that. So suppose the speed of a given parameterization is constant. Oops, sorry, I need speed there. So sorry, I didn't say speed. Suppose the magnitude of a position vector, so r as a constant magnitude. So suppose the magnitude of the position vector is always constant. By the way, folks, in 3 space, what would that mean? If you thought of the position vector as starting from the origin in 3 space, if you can't change the length of that vector, that black vector in 3 space, what are you going to be tracing out as you move along any sort of curve? You're always going to be sitting where?
On the surface of a sphere?
Always on the surface of a sphere. Okay? Meaning if you can't adjust so remember what we're saying here, this is saying you can't adjust the length of r, only the direction. So in 2 space, that's saying, that you're on a circle. If you think of these as position vectors from the origin. Now, I'm not saying necessarily that your curve is a circle, but it would trace out always, the trace of it would always be on a circle. And in 3 space, that's saying that you've got a constant radius, and you can move in different directions, but your magnitude can't change. And so that puts you always on the surface of a sphere. Okay. So let's go ahead and show then that the velocity vector is always perpendicular to the position vector when that's the case, because we're going to need that fact down the road here. So the first thing is if this is the case, I can square both sides, and that would give me that information. But what if I square the magnitude of a vector, what does that give me? So let's just, if you're rusty on that, let's check that. If I gave you R of t is equal to, 3, well, let's just say R is equal to 3, 2, 1. If I squared the magnitude of R, what's that going to give me, folks? Well, it's going to give me the square root, because the magnitude is the square root of 3 squared plus 2 squared plus 1 squared, right? And if I square that, that gives me 3 squared plus 2 squared plus 1 squared. But another way to look at that is that's 3 times 3 plus 2 times 2 plus 1 times 1.
Dotted with itself?
Exactly. Okay. So when you square the magnitude, what you get is just the original vector dotted with itself. Okay. The next thing I want to do is go ahead and take the derivative of both sides with respect to time. So on the right-hand side, we're going to get something, but what for sure are we going to get on the, on the left-hand side, we're going to get something. What for sure are we going to get on the right-hand side of this, folks?
0.
We're going to get 0, because it's a constant. And on the left-hand side, we would have, so we had a product rule for the dot product. It was called the dot product property, but it's the dot product rule for differentiation. And that said that you would take, leaving everything in the same order, you'd have the first dotted with the derivative of the second, plus the second, or sorry, I got to stay in the same order, plus the derivative of the first dotted with the second. Any questions about that? Let me zoom in on that. Sorry, that's so small. Can you see that okay? What's another way, though, of talking about the derivative of the position vector? What's another way I could write that?
Velocity vector.
That's the velocity vector. So we got r dot v dot, I heard a couple of you say that, plus v dot r. But what do we know about the dot product? It is symmetric, meaning I can, even though I should be, from here on out I should always be careful with the order of things. A dot b, vector A dotted with vector b is the same as vector b dotted with vector A. It gives you the same value. So I can reorder this as r dot v plus r dot v. And now I'm adding them together, so I got 2 r dot v. And if I divide both sides by 2, then I get the fact that r dotted with v equals 0. But what have I just shown, folks? I've just shown that if I have a constant, a position vector of constant length, then it will always be perpendicular to its velocity vector. Okay. And I don't work a whole lot of proofs in here, but I thought that one was a nice one, especially since in class we basically derived that rule. So I thought it was nice to actually put that into application with one of these proofs. Okay. Look great. Okay, folks, we're a little bit long. I was hoping to get into the arc length today. We did not get there, so that's on me. Okay. let's go ahead and take a break here. We'll start up here at 2:26. And when we get back, I'm going to give you guys some time to work in groups, talking about questions that you had on the exam review. And then we will take those questions as a class all together when you get back, or when we get back into the main room. Okay. So please be back here at 2:26, so I can put you into your breakout rooms. All right, folks. We'll see you soon. If you have questions, feel free to stick around, though. I'll answer them.
I'm still kind of confused about the 150 root 3 on question 3. So, so I understood how you separated it between ground and air, the two vectors.
Oh, hang on real quick. Sorry, let me pause the recording.